in the last part we have discussed about potential method, and we see the example of stack operations, right? And we perform amortized analysis on the stack operations using this potential method. In this part we are going to see the other example, which is binary counter, and we are going to perform the amortized analysis on the binary counter using the potential method. Okay, so as you know that for any potential method, or heart of the potential method is a potential function, right? So what could be the potential function for binary counter? So we can define the potential function of of binary counter to be the number of ones in the counter. Okay, so the number of ones in the counter is going to be our potential function. So initially when the counter starts, right, we, as you know, that we are considering the counter starting at 0, right? So initially when the counter starts at 0, there will be no ones, right? So the, as per the definition of the potential function, the phi of d0 will be 0, because there will be no one in the binary counter initially, right? Now we can also tell that phi of di means the potential of the data structure after ith operation, I be the any non-negative integer, will be cannot be negative. Okay, because the number of ones in the binary counter can never be negative, right? The count of one in the binary counter can never be negative. So whatever operation you perform on the data structure, after any operation I, the phi of di is going to be greater than or equals to 0. Okay, because the negative number of ones is not possible. Okay, so what we found from this two analysis, we found that therefore the phi of d0 is less than or equals to phi of di for all I, right? So it means that it assures the upper bound of the amortized, of the actual cost by the amortized cost, right? So you can remember from the previous part that if phi of d0 is less than equals to phi of di for all I, then the actual cost is going to be upper bounded by the amortized cost of the operation, right? So here this we have proved that this is going to be, this condition is going to hold, or this condition is true, right? So what will be the amortized cost of the increment operation? So again, if you look at the explanation, or look at the analysis we have done till the point, you can see that we have not assigned the amortized cost yet to the increment operation. Rather, we have defined the potential function. Okay, so let us see what will be the amortized cost for the increment operation. So you know that, in case of binary counter we have only one operation, right, which is increment. So any sequence of n operations will have only n increment operations over there. Okay, now so to find out the amortized cost of increment operation, let us do the following steps. Okay, so let us define bi as the number of ones in the counter after ith operation. Okay, so we are defining bi as the number of ones in the counter after ith operation. So that is nothing but the potential of the data structure after the ith operation, right? So that is nothing but the phi of di, right? So this is phi of di is nothing but bi. Okay, so bi is your potential of the data structure after ith operation. Now let ti be the number of bits that are being reset during the ith operation. So so ti is your bit reset, right? Reset means we are converting from 1 to 0. Okay, so we are making 1 to 0, right? So let ti be the number of bit reset during the ith operation. So since we are resetting, means we are converting from 1 to 0, it also means that after the ith operation, the potential drop, right, of the data structure will be ti, because we are making, in the ith operation we are making ti number of ones to 0, right? We are resetting ti number of bits. So it means that the potential drop of the data structure after ith operation is going to be ti. So we can also tell, you can also understand from this that the actual cost of the ith operation is going to be ti plus 1. Why? If you can remember the definition of the definition of the increment operation, what we have there, we have a loop where we are basically resetting the bits, right? We are basically making 1 to 0 in that loop. So we are considering over here that we are having ti number of bits which are basically resetting, and there is one bit which we are basically making from 0 to 1, right? So the actual cost is ti number of resets plus one set. Okay, one bit we are making from 0 to 1. Okay, so that is what your actual cost ci is. Okay, so ci is nothing but ti plus 1, number of bit reset plus 1. Now, if bi is equals to 0, means after ith operation, if we found that bi is equals to 0, means there is no 1 in the counter. What does it mean? It means that after ith operation, we have converted the counter. The state of the counter is all zeros, right? Because since they, if bi after ith operation the value of bi is 0, it means there is no one, because bi is denoting the number of ones in the counter. Hence all the bits in the counter has become 0. Now when it is possible, it is possible only if the prior to the ith operation all the bits were 1, right? It is possible only when prior to the ith operation all the bits were 1. So that means that all the bits at the I prior to the ith operation, means bi minus 1 will be 1. So we are considering a k bit counter, right? So bi minus 1 is going to be k. Okay, and that all the ones are converted into 0 in that ith operation. It means that ti will be k when bi is equals to 0. Okay, we are considering ti is the number of bit reset that are the number of ones that are converted to 0, right? So if we found that bi is equals to 0, it means that prior to this ith increment call, we have all the bits was set to 1, right? And then we perform this increment call and it resets all the bits, means it is converting 0 all the bits, right? Or from 1 to 0. So it means that the value of ti is going to be the number of bits in the counter is k. Okay, so bi minus 1 is equals to k is equals to ti minus ti. Okay, so now we can tell that bi less than equals to bi minus 1 plus minus ti plus 1 holds. Why? So bi in this step we have bi is equals to 0, right? Now bi minus 1, what we have in bi minus 1, bi minus 1 from here we can tell that bi minus 1 is nothing but k, right? Minus ti. Also from this statement we can find that ti is equals to k, right? And next we have plus 1. So we have this bi minus 1 as k, we have ti as k, and we have this plus 1 over here. So this k will be cancelled out, k and minus k. So what we have in the left side we have bi is equals to 0, and in the right side this expression is returning us to 1, right? So 0 less than equals to 1 is true, right? So that condition holds. Now if b greater than 0, so if b greater than 0, then the case is a bit easier. So sorry, if bi is greater than 0, it means that then the number of ones in the bit will be what? So so bi minus 1, before the ith increment call we have bi minus 1 number of ones in the counter, right? Then we have ti number of ones that are reset to 0, right? So we will be reducing the count of 1 by ti, because we are resetting ti number of bits, and then we are also setting 1 bits, right? We are also setting 1 bits. That will be only when for the other cases, right? When bi greater than 0. Okay, so then we will have bi is equals to bi minus 1 minus ti plus 1. Okay, so for these two cases, bi less than 0 cannot be possible, so we have only these two cases. Okay, for bi. So for these two cases, we have found that here bi less than equals to bi minus 1 plus minus ti plus 1, and here we are finding that bi is equals to bi minus 1 minus ti plus 1. Okay, so together we can tell that bi is nothing but less than equals to this bi minus 1 minus ti plus 1. Okay, in both the cases we can tell that this inequality holds. So what we can derive from it? So now we will determine the potential difference after the ith operation. Okay, so the potential difference after the ith operation is phi of di minus phi of di minus 1, right? So this is nothing but bi minus bi minus 1, because potential difference is nothing but the number of ones in the counter, which is denoted by bi, right? So the potential difference phi of di is equals to bi, and phi of di minus 1 is equals to bi minus 1. Now so from this inequality we can write that this is less than equals to, so bi is replaced with this one, bi minus 1 minus ti plus 1, and this bi I minus 1 was there, so this is that bi minus 1. Okay, so now if we find out, so this whole expression is equals to 1 minus t, right? Because this bi minus 1 will be cancelled out, so we'll be left with 1 minus t, 1 minus ti. Okay, so what we can tell? So we can tell the amortized cost of ith operation is as you know that it is basically actual cost plus the potential difference, right? So amortized cost of ith operation is c cap I is ci, that is the actual cost for the ith operation plus the potential difference. So we have found that the actual cost is ti plus 1, and we also have found that the potential difference is 1 minus t, right? So if you replace those values over here, I mean sorry, potential difference is less than 1 minus, less than equals to 1 minus t, so we can replace the value over here, and we can found that ci is replaced is by this one, and the potential difference by this one. And if you further do it, I mean do the mathematics, you will, it will cancel the ti out, and we will be left with 2, okay, which is order of 1. Now if you think in case of binary counter we only have one operation, right? That is increment. So whatever be the value of I, all the ith operation is going to be increment operation. So the amortized cost of any ith operation is denoting is nothing but the amortized cost of the increment operation, right? So that is nothing but the order of 1. Okay, so that is the discussion of the binary counter. I mean we perform the amortized analysis of binary counter or the operation increment operation of the binary counter using potential method. In the next part we are going to or in the next lecture actually we are going to discuss about elementary graph algorithms.